Now I want to show you another thing which we've already seen before. So a lot of these techniques, okay, the techniques we just looked at with sine and e to the x's and trigonometric functions and stuff, they're using this idea that if you know what the original function was, and if you differentiated it, then you can get here. So it's almost like tracing your steps back. You're saying, what function, when I differentiate it, gives me this new function? That's what another way to think about integration is, okay? Now, can I draw your attention to this one here? Okay, 1 over x with respect to x. Now, at first, you look at this and you go, this looks like a polynomial function because I can rewrite it as x to the power of
x
minus 1.
Sorry.
Okay, minus 1.
Derivatives.
Okay, yeah, good, good. That's what I'm asking. Okay, and then I just go ahead and do this. So if this was a polynomial, it would become x to the power of negative 1. You're like, because I can write it as x to the power of negative 1, all I need to do is raise the power by 1, then divide by that new power. So let's give it a go. So raise the power by 1, I get 0, okay? And then divide by that new power. Problem. What's the problem? I'm dividing by 0. What is anything divided by 0?
Undefined.
It's undefined, yeah? It's undefined. Because you're literally asking here, how many times does 0 fit into that thing? Answer, as many times as you like. It doesn't really have a meaning, okay? If you really know what you're doing, it could be plus or minus infinity. So clearly this starts to break down, okay? I need another way of thinking about it. Well, that's okay, because wasn't there a function which when I differentiated it, got me 1 over x? Yeah, good. So I know this thing, because I know what function I differentiate, must have to be natural log of x. Of course, I'm putting the plus c there because there could have been some number there beforehand. Does that make sense? Yep. So really, another way to think about integration, or the way to think about integration in this case, is to say, well, what function, when I differentiate it, gives me this? And I can sort of trace my steps back. Yes. Okay? So let's have a think about this in a little bit more detail. Okay? If I asked you to differentiate, natural log of x squared plus 4, okay? What would this thing be? What's the derivative of the natural log of x squared plus 4? 2x. Yeah? X squared plus 4. You happy with that? Happy with that? We looked at it's just literally the chain rule. Natural log function just means 1 over, leave that function alone, multiply by the derivative of that. Does that make sense? So have a look. Have a look. What I've really got here is my original function inside the natural log. Okay, that's my original function. So if I call that f of x, that's my original function. And that ends up on the denominator of that fraction. Happy with that? Okay. Now what goes on the numerator of that fraction? By definition, because it's the chain rule, yeah, I have to multiply by the derivative of that function. Hence it ends up on the numerator. Does that make sense? Does that make sense to everyone? Yeah. So if I differentiate the log of some function, that should be equal to the function on the denominator and the derivative of the function on the numerator. Which means that I can use that fact when I'm doing my integrals. Okay? So if I'm integrating something like 3 over 3x plus 4 with respect to x. Okay? Have a look. This looks a bit awkward, doesn't it? Looks a bit awkward, right? But if I just make use of this fact, that if I have the function on the denominator, so I have, this is my function, 3x plus 4, okay? And on the numerator, what do I have? The derivative of that function. Yeah, because you're happy the derivative of 3x plus 4 is 3, then I can make use of the fact that if I have the integral of a function on the denominator and the derivative of the function on the numerator, by remembering this idea, that should be equal to the natural log of that function, of that 3x plus 4. Literally just thinking about where I've come from. I'm saying, what function, this is saying, what function, when I differentiate it, gives me that? And it's got to be that. Does that make sense? Yeah? So in other words, in general, if I have the integral where I have the function on the denominator and the derivative of the function on the numerator, that should be equal to the natural log of that function. Because I know about the fact that integration and differentiation are just reversed of each other. It's kind of like, this is the answer, this must have been the question. All good? Yeah, and vice versa. Okay, fine. So, have a look at the next one. Because the next one isn't quite that. So, this is question 2. Okay, this is question 2. So, question 2 didn't have a 3 there. It had a 5 there. So here's my question. How does that change things? Good-ish, almost there. I want a 3 there, don't I? I want a 3, because if this condition was going to hold, I'd want a 3 there, because then it'd just be 3x plus 4, the derivative of 3x plus 4.
So it will be like 5 over 3, multiply and then 3x over plus 4.
Absolutely right. So because I want a 3 there, why not put a 3 there? Okay. In fact, let's get rid of that 5, because the 5 doesn't want to be there at all. So let's take him out the front. Get him out of the way. Put the 5 there. I want the 3 there. Don't I? So in order to just put a 3 there, I can't just stick it there because I feel like it. I'm going to have to divide by that 3 out the front. Is that okay to everyone?
Yes.
Yeah, does that make sense? So in other words, now I have the condition that this holds, this thing over here holds. So I'm going to have the natural log of 3x plus 4. Okay? But I'm also going to have this coming along for the ride as well. 5 over 3. Does that make sense to everyone? Yes. What we've done there? Yeah? So it's a bit of a fudge. It's exactly the same thing we were doing before. It's a bit of a fudge. I want a 3 there, so why not put a 3 there? But in order to stick a 3 there, I'm going to have to divide by it here. Is that okay with everyone? Can you ever get question 3 for me then? So, it looks quite horrible, doesn't it? But what I want to get you in the habit of is whenever you see the integral of a fraction, always check whether this condition holds. Because 9 times out of 10 it probably will. Or at least you can make it look like it will. Okay? So, let's have a look at this. Okay? At the moment, I'm saying that my function, my f of x, is that denominator. Now, what should the derivative of that function be? If I just differentiate that, what do I get? 8x cubed minus 5x to the power 4, yeah? Plus 0, okay? Now, is that the same as that? Yes, it is. So therefore, this big, horrible thing actually is quite simple to solve, yeah? What should it be equal to? Natural log of? Yeah, that function there, right? Good. Don't forget your plus c. Is that good? Any questions? Okay. Now here's a challenge for you. Okay. What would this thing be? Let's do it together. We looked at the derivative of tan x. What would the integral of tan x be? Yes. Absolutely. So the idea here is you need to rewrite tan as sine divided by cos. Okay. And then, just that thing, isn't it? Just that thing. Because if your function is cos x, what's the derivative of cos x?
Sin x.
What's the derivative of cos x?
Minus sin x, sorry.
Right, so I want it to be negative sin x, don't I? I want it to be negative sin x, then that would hold. So I want a negative there, so I'm going to have to stick a negative out the front there. Does that make sense? Yeah, so my function is cos x. The derivative of my function should be negative sin x, so I need to make that negative. But I can't just make a function negative for the fun of it. I need to make sure that I cancel it out at the front. Okay? So my fudge is negative. So therefore, now this thing holds. So it's going to be negative natural log of cos x plus c. So the integral of tan is negative ln of cos plus c.